Hi guys, let's look at stereochemistry. Here's our stereochemistry outline. We also have the stereochemistry handout set, which begins with warm-up questions. Also included here is the DQ page, which was posted separately. And then a variety of miscellaneous sort of handouts that we can reference as we go along. And we'll actually look at this page here with this photo early on here. Now I'll give you a sort of a brief discussion, my discussion of the idea of chirality, okay, which is a very important concept related to stereochemistry. Basically, stereochemistry begins with the idea of chirality. It's also known as handedness. We will explain that. Okay, I'm not going to read this paragraph to you. As I make statements here, those statements will likely be in this paragraph. So it's a sort of a summary paragraph. Now, stereochemistry is very important. Chirality is very important. Let me give you some suggestions as to why. If we look here, for example, this shows cellulose, structure of cellulose. It's a polymeric. Okay? And starch, very similar. They're polysaccharides. You'll learn that terminology more, particularly in biochemistry. The only difference between cellulose and starch is stereochemistry. And if you look at the glycosidic linkage between the saccharides, the sugar rings, the carbon-oxygen bonds, in cellulose, one of the bonds is equatorial. Actually, both of them are equatorial. But in starch, only one of them is equatorial. The other carbon-oxygen bond in the linkage is axial. And that is just stereochemistry. The oxygen is connected to that carbon in both cases. So they have the same connectivity. It's just the orientation of that bond in space is different. Same connectivity, all right? Different orientation in space. Or we can say a different 3D arrangement. Now that is actually noted down here in this schematic, which is a very important summary. Types of isomers. There's two types, constitutional isomers, and we have defined that earlier. These have different connectivity, okay, and thus different name. Stereoisomers have same connectivity. All right? That's what this implies. This way is different connectivity, same connectivity. We can state that. Same connectivity and same name. All right. As we've noted before, stereoisomers, the name only differs by having a different stereochemical descriptor. For example, cis or trans. We will learn other stereochemical descriptors, RS, D or L, erythro or threo. Now there's actually two types of stereoisomers. Enantiomers, which are mirror images, and which we will begin talking about here very shortly, or stereoisomers that are not mirror images. Those are called diastereomers. And actually cis and trans is a type of diastereomer. Those are diastereomers, a diastereomeric relationship. All right. Make sure you understand why cis and trans are considered diastereomers. Okay, another reason illustration of the importance of stereochemistry. Back in the late 1950s, early 1960s, a drug by the name of thalidomide was given to pregnant women to treat morning sickness. That drug was named thalidomide. Thalidomide exists as two enantiomers. Okay. The two mirror images, which are different. And it turns out that one of the mirror images was a safe and effective drug. The other mirror image was actually toxic, and it caused severe birth defects in the developing fetus. Many of the pregnancies were unsuccessful or aborted because of the drug toxicity, miscarriage, etc. Fetuses that did develop and with babies being born, many of them had severe birth defects, such as missing appendages, such as missing arms. And this shows a photo of some of those young children. Now eventually this problem was discovered and corrected. Actually, there was a nurse in the United States that helped bring attention to this and solve this issue, and that nurse received a medal from President Kennedy. Okay, if you're interested in more of the story of thalidomide, you can look that up. Very interesting. Lots of organic chemistry here. Let's look closer at stereochemistry. Handout. Let's begin by taking a closer look at an asymmetric chiral carbon. All right. Now, chiral carbon is one that has 4 different groups attached. An sp3 carbon with 4 different groups attached. Is that stated above? Yes. I think third line. 4 different substituents in a non-planar arrangement, and that's typically an sp3 geometry. All right. A chiral carbon. And that's what we have right here in this fairly small molecule. Many times chiral carbons are indicated with a little star or asterisk. This carbon has 4 different groups attached. A bromine, a chlorine, a methyl, and an undrawn hydrogen. It's also non-planar. It's sp3 tetrahedral. Thus, it is an asymmetric carbon, or aka a chiral carbon. Thus, this carbon here with the 4 groups, or this molecule, or more correctly, the bonds around that chiral carbon can exist in 2 different configurations. Okay? 2 different configurations. We will draw those. Now this is going to be analogous to your hands. Okay? If we put together sort of a template with 4 fingers like this, a pointy finger, an index finger, a ring finger, a middle finger, whatnot, a pinky, and a thumb over here. If we put this together like this, you will actually find that you can build such an arrangement 2 different ways. This way or this way. Okay? I have a thumb sort of to the side of a pointy finger. Thumb to the side of a pointy finger. It's the same configuration. Well, no, that's not right. It's the same connectivity, but they're configured just sort of differently, and actually they're configured as mirror images. And that's the two different configurations you can have for this arrangement. You cannot have a third. I've never seen any other type of hand, unless we call it maybe a deformity. But only two types of hands are known to exist. And when we have the same thing with chiral molecules, only two different forms are known to exist. By the way, this is why chirality is also called handedness, because it's analogous to your hands being different configurations. Okay, let's draw the different configurations, the two possible configurations of this molecule, and we will do that by drawing the tetrahedral nature. Let's see if I can do this without having to erase. Okay, let's put boom. There's the bromine in this methyl, but let's put the chlorine. Okay, that's two in the plane. Let's put the chlorine forward. All right, because it is tetrahedral, right? Let's draw the exact tetrahedral nature. And let's draw in the fourth bond, and it is to an undrawn H. And it would thus have to be going back here. All right. Now I'm going to continue or approach this discussion by next drawing the mirror image of this. Mirror image. That is, if this looked at a mirror, okay, if this was a mirror, you look at a mirror, what would this see in the mirror? Well, it would see this. I'll make that a little bit longer because I made that a little bit longer. Now there will always be slight differences in my drawings, but hopefully you see that if this looked in the mirror, it would see that. These are mirror images. Okay? Now everything has a mirror image. Except maybe a vampire. So having a mirror image doesn't mean much. The question is, are these two mirror images the same or different? And these are different. Okay? Mirror images that are different. It's two different mirror images. How do we know they're different? Well, there's multiple ways. The first way is, well, how do you know your hands are different? Well, this one will only fit into the right hand glove. This one won't. But the more kind of straightforward way is to say, okay, if they're the same, we should be able to stack them on each other. All right. Stack them. I was looking for something I could stack. My hands, okay. You cannot stack them. If you try to stack them, you'll have one thumb over here and one thumb over here. All right. And we say that these two compounds, well, my hands are not superimposable. All right. Well, these two compounds are not superimposable. So what we have here is two different non-superimposable mirror images as a result of the chirality, the chiral nature about this carbon that we identified here. Now, can we show they're not superimposable? I tried to show with my hands. Let's, okay, here's one here. The bromine is blue. Bromine is straight up. Carbon is black coming to the left, straight. That's this, okay. The H is going back. It's small, okay. Chlorine green coming forward. All right, this is this molecule here. Actually, if I set it down, there we go. Here's the plane. Bromine straight up, carbon over here. H going back, chlorine coming forward. That's the first one, right? Mirror image. Okay, is this the mirror image? Let's see. We want that up. There we go. Okay. I'm going to turn it so you can see that H. There we go. Okay. There we go. Are those two mirroring? It looks like it to me. I'm looking at the same thing you're seeing. All right. Yes. They're the two molecules we drew. Are they superimposable? Can we stack them? Well, let's bring this image over here. Okay, like an image that can just move in there and stack. All right. Well, the blues line up, the H's line up, but look, the black and the green, the methyl and the chlorine, methyl and chlorine. All right, the two chlorines are not lining up. The two methyls are not lining up. Well, we can turn that and make the two methyls line up and the two chlorines line up. But now the H is lining up with a bromine. Okay, the two bromines are not lining up. If you switch those back, now the bromines are lining up, the methyls are lining up, but the two chlorines are not. Ultimately, they will never all line up. They will not be superimposable. These two compounds are different, just like your hands are different. They're called enantiomers. Okay? All right? Called enantiomers. Now, hands, we call this one the right hand, this one the left. Well, what can we call these two? Well, two different ways to do that. One is going to be R or S, okay? Two different ways to distinguish enantiomers. The other is D or L. I will start with the R and S. R and S is where you identify the configuration around an individual chiral carbon. Okay? Individual, well, that's chiral compound. Down here, an individual chiral atom or carbon designated as either R or S configuration. Let's do that. The way we do that is first give priority to the four groups on the carbon. Priority is given the same way that you do with EZ alkene terminology. Highest atomic number would be bromine, that'd be 1. Next would be chlorine. Then carbon would be 3. And H would be 4. And with the highest priority group in the back, all right, and I've stated that incorrectly. Lowest priority group in the back. Let's write it down so I don't misspeak. Lowest priority group back, we then look at the 1, 2, and 3. Are they going clockwise or counterclockwise? And the 1, 2, or 3 is going clockwise, and that is the R configuration. Now, I will tell you this already. The mirror image of R is always S. So I'll bet you a steak dinner that this one is S. Well, let's do it. Bromine is 1, chlorine is 2, methyl is 3, H is 4. The lowest priority group is going back. And we see that the 1, 2, 3 is counterclockwise, and counterclockwise is indeed S. Yes, free steak dinner. And so both of these compounds are 1-bromo, 1-chloroethane. But one of these is R, and that's typically in parentheses, then the name. The other is S, and then the name. We have a stereochemical descriptor to distinguish between the two stereoisomers. Now, before we move on, let's try something here. I'll try a piece of paper. Let's try first I'll do this. I'll put the bromine there. Boom. Boom. And put the chlorine there. Okay. This looks like 1-bromo, 1-chloroethane. Hopefully you agree. What's the relationship between this compound and these two here? Is this a third stereoisomer? Well, the answer is no. A chiral carbon can only have 2 configurations. We have them both here. This is actually one of those up there. Which one is it? Well, let's do RS configuration and then we can tell which it is. Bromine 1, chlorine 2, methyl 3. Okay, where's the fourth group? Well, it's coming forward. Okay, you don't have to draw it in. We know it's coming forward, fourth. This is 1, 2, 3 is clockwise, but the low priority group is not going back. The low priority group is forward. If that's the case, just reverse your answer. Okay? And so instead of calling this R, we reverse that, and this is S. And thus this is S. And if you name it, it's the same name. And thus this compound and this compound, which are both S in the same name, are the same compound. All right. So I told you how to do RNS with the low priority group coming forward. What about something like this? Now I'm going to draw the chlorine up there because I can draw this a million different ways. I'm going to put the H here. Let me put the bromine back and the methyl group forward. That's kind of big. Now this looks kind of like, well, what should be there? So I'm just going to clarify that it's a methyl group. Okay, what is this? Well, it's the same name as all the others. If you name it, there can only be two configurations. What is this? 1, 2, 3. Low priority group in the plane. Okay. How do we do that? Now, stay tuned. Some books will tell you ways to do that. I will tell you my recommendation for how to do this. We will go to a Fisher projection needed. Okay? All right, we'll get there. We're not ready to do Fisher projections. Let's come back over here. What about this molecule? What if we have two bromines instead of a bromine and a chlorine? Enantiomers of that? No. Okay. That is, if we drew this and maybe then drew this. Okay. Those are mirror images. Yes. So they are mirror images. But these are not different. All right. Now if I take my models and replace chlorine with bromine, a second bromine, and then we have bromine in the plane. I've got the plane up like on the board. One bromine forward. That bromine forward and an H, undrawn H going back. And then if I show the mirror image, that would be come on. There we go. Now they're mirroring each other. Same or different? Well, can you superimpose them? All right. We try to line them up. These two bromines are lining up. The two H's are lining up. Uh-oh. Those two are not, and those two are not. But guess what? Okay. All I've got to do is turn them around a little bit. And there you go. Look at there. These two bromines lining up, these two bromines lining up, these two methyls lining up, the two H's are stacked. Those two compounds are nicely superimposable. Those are the same two compounds. Okay, same. This compound does not exist as an enantiomers. Why? Because no chiral carbon. Or more broadly, no site of, how do you spell site? That doesn't look right. No site of asymmetry. Chiral carbon is a site of asymmetry. That's going to make the entire molecule asymmetric. In asymmetric compounds, the mirror image will be different. This compound has more symmetry. Okay? Let's actually convert this or change this over to this compound has a plane of symmetry. Can we find it? Right there it is. Okay? Right through here is a plane of symmetry. Okay? Right through here. We have a bromine on one side, bromine mirroring on the other. And if we come right through here, we'll split half an H going back with half an H going back, half a methyl going forward, half a methyl going forward. Or we can do this way. Well, that's not a plane of symmetry, because if you cut right through here, you'll have an H on one side and a methyl on the other. But right there is. Okay? If we go back to the compound with the chlorine on it, that is not a plane of symmetry. You'll have a bromine on one side and something different on the other. And that is not a plane of symmetry. This compound has no plane of symmetry because of the presence of one chiral carbon. Now I won't kind of keep going here. We will build upon this and add more to it. But this is very important because later on we'll look for planes of symmetry. Sort of like Where's Waldo. This compound has, it has a plane of symmetry, thus it's not chiral. Not chiral. Okay? Alright, let's move ahead. Pause the video, take a drink of water. Now, we can say that enantiomers have identical physical properties, such as melting point, boiling point, dipole moment, density, etc. Why would these two different molecules have similar or identical properties? That's because they have the same arrangement of the groups in space. If you drew a dipole moment here, you would have the same discussion over here, it would just be mirrored. They have the same solubility, they have the same IMFs that are possible. It's just, the molecule is just kind of inverted as we go from one to the other. Identical physical properties, with one exception, or possibly two. The main physical exception is they rotate plane polarized light in equal but opposite directions. One enantiomer will rotate plane polarized or PP light one way, and the other enantiomer will rotate that PP light in an equal but opposite direction. Now the one that rotates PP light to the right, or the positive direction, is called the dextrorotatory isomer, or D. The one that rotates PP light to the left, which is known as the negative direction, is called the levorotatory isomer, or L. All right. Now, why does one rotate light one way and one the other? Consider my hand, and if light was coming in here, okay, light is a form of electromagnetic radiation. Molecules both have electronic properties and magnetic properties. They will interact. Okay? Now suppose that this group, the thumb group, sort of alters the light path and makes it turn towards the thumb maybe, or maybe away from the thumb. But let's say it makes the light turn away from the thumb. So the light comes in here and it's pushed away, and that's to the right, away from the thumb. With this molecule, the light is pushed away from the thumb, but it would go to the left. And that's why you get two different directions. Now, if the molecule was symmetrical, and maybe you said, well, the blue group is going to make the light move to the right, and well then, if the light comes through here, if this makes it move to the right, and then the other group makes it move to the right, you're going to get no net movement, and the light will just come straight through. Now importantly, R and S designation has nothing to do with D and L. One is based solely on structure, the other is based on an observation or experiment of the rotation of the PP light. Now as I just alluded to, with a non-chiral or an asymmetrical molecule like this one, we can call achiral. Achiral compounds do not rotate PP light. That is, they are not optically active. Now, enantiomers also interact with chiral objects differently. Now, a simple example of this is these chiral objects interact with chiral objects differently because only this one will fit into the right-handed glove. Only this one will interact with the right-handed glove in a certain way. That's an example of a chiral object. This is a chiral object interacting with another chiral object. The glove is also a chiral object differently than how this one interacts with the right-handed glove. Now, in terms of chemistry, this is important. The same analogy applies to drug interactions or drug receptor interactions. And that's actually shown on the handout over here. Sort of an example of that here. Okay, let's look at optical rotation for enantiomers of 2-butanol. All right. And bring in the idea of rotation. First off, let's draw the two enantiomers of 2-butanol. Boom, boom, boom. Here's your chiral carbon. We can throw in, include some precise stereochemistry. How about if I make that like that? Enantiomers, mirror images that are different. Let's draw the mirror image. Okay. I'll do it as mirrored. Boom, boom, boom. Do those look like they're mirroring? I say yes. Let's identify the configuration of each chiral carbon. Oxygen is 1. Carbon or carbon? Well, this carbon has another carbon on it. If you remember for E or Z, we said, well, what's on the group? This carbon has a carbon H and H. This carbon just has H, H, H. And so right here we get a winner. Carbon beats H. A longer alkyl group is always going to be higher priority over a shorter alkyl group. So this is 2, this is 3. The undrawn H is going back. Clockwise, this is R. This, I guarantee you, is S. You can do it on your own. Here are the two enantiomers of 2-butanol. Now the rotation, that specific rotation of pp light for the S is positive 13.5 degrees, and for the R is negative 13.5 degrees, equal but opposite rotation of pp light. All right. Thus, the S enantiomer, we can call it S2-butanol. We could also call it D2-butanol. Because D is the positive rotation. We can also call it positive 2-butanol. Where with this molecule, this would be called the R enantiomer, or the L2-butanol, or the negative 2-butanol. That's my L. So we thus have different stereochemical descriptors for enantiomers now. These are based on the rotation, where the R and S is based on the configuration around the chiral carbon. Now, by the way, when I drew the enantiomer of this, I drew it as mirrored. I could have drawn it, and this is very important. Well, first off, let me just ask you, what is this here? The alcohol group is also at the 2 position of the butane. We call this 2-butanol. You'll learn alcohol nomenclature in Organic 2. But which one is it? Which enantiomer? This is S. Okay? These two are the same. Very important. Here's the take-home. If you have a chiral carbon, you can get the enantiomer 2 different ways. You can draw the configuration mirrored, as I did originally, or you can just switch your projection from bold to dashed or dashed to bold, but keep the backbone the same. Keep the groups the same position. Okay? The backbone is the same. The OH group is on the second carbon from the left, just like this. I just switched the projection. That will give you the other configuration. And that's how I will typically do it in class. I will stop trying to draw things mirrored. Okay? Prove to yourself that this is S. Okay, some homework here. Please think about the homework questions. Particularly this one here. Get back to our reactions and terminology here. Okay? This will require some scratch paper. I would do it on scratch paper. In the next video, one of the next videos, we'll get into topic B here, more about optical activity of an antiomeric mixtures. We'll be then moving ahead, and one of the future videos will also focus on Fisher projections. And there's a variety of miscellaneous things for us to discuss throughout this handout. Here's a brief history of chirality, how the idea was discovered, Louis Pasteur, his role, and in the back is some of our lecture material. So please be looking ahead in this handout, and as well as the other supplementary handout. Okay, guys.